All right, so we're diving into the Reynolds number today. All this material you sent over looks really interesting. We've got the Wikipedia article, which is, usually a good place to start. I got to ask, though, what made you want to deep dive into this? What is it about the Reynolds number?
Well, the Reynolds number, it's really all about versatility. It's this dimensionless quantity. So we're not talking meters or seconds or anything like that, but it can predict how fluids behave in all kinds of situations, whether it's water flowing through pipes or air over, like an airplane wing.
So you're saying no matter the fluid, no matter the situation, the Reynolds number can tell us something about the patterns.
Exactly. And what's really interesting is that it basically comes down to a tug of war between two forces, inertia and viscosity. Inertia, that wants to keep things moving straight, and viscosity, that's all about resistance, like trying to stir honey with a spoon.
Okay, yeah, I can see that.
Yeah.
So how does this, like tug of war, how does that play out in an actual fluid?
Okay, so imagine a nice, smooth stream of water flowing through a pipe. That's laminar flow. Viscosity is winning that tug of war. Everything's nice and orderly. But let's say you crank up the flow rate. And now those water molecules, they're bumping into each other, more and more. That's where inertia starts to win, and the flow becomes, well, chaotic, turbulent.
I'm picturing like a highway where
Oh.
cars are moving along smoothly at low speed, and then all of a sudden everyone's trying to merge, and it's just like a chaotic mess. So the Reynolds number tells us if we're in that smooth flow or rush hour madness.
Exactly. And that transition, that's the magic of the Reynolds number. Like in pipe flow, that magic number, it's around 2300. Below that, laminar flow. Above it, get ready for turbulence.
Okay, so that's why it's called a critical Reynolds number. It's like a tipping point. But why does any of this matter in the real world? I mean, why should we care if a flow is laminar or turbulent?
Well, let's stick with pipes for a second. Imagine you're designing a system to transport water. If you can keep the flow laminar, you're going to save energy, right? Less friction. But if it becomes turbulent, well, all that chaotic movement, you're losing energy.
So knowing that critical number, like 2300, helps engineers design those pipes to be more efficient.
Yeah, exactly. But you mentioned that Reynolds number applies to more than just pipes, right? What about those airplane wings you're talking about?
Oh, right, airplane wings. I'm guessing that's where the Reynolds number gets aerodynamic.
It does. You see, engineers can't always build full-scale models of airplanes to test in wind tunnels.
Yeah, good luck fitting a Boeing 747 in a wind tunnel.
Right. So they build scaled-down models. But how can they be sure that the airflow over a tiny model is the same as what's going to happen with the actual jumbo jet? That's where the Reynolds number comes in.
So they use it to make sure the tests in the wind tunnel are accurate. For the real plane, I mean.
Yeah. They match the Reynolds number between the model and the full-scale aircraft by adjusting, airspeed and scale, making sure that that ratio between inertial and viscous forces, that it stays the same. This way, engineers can test, like different wing designs, and predict how they'll work in the real world really accurately, too.
Wow, that's really clever. It's like a cheat code to translate between that tiny scale and, jumbo jet. So thanks to the Reynolds number, we can test things on a tiny scale and know they'll work when they're huge. I'm starting to see why you said this concept is so versatile. But you also mentioned it shows up in other places, too. What else? Tell me more.
Well, think about a golf ball flying through the air. Why does it have all those dimples? It's not just aesthetics.
I'm guessing it has something to do with airflow.
It does. Those dimples, they actually manipulate the Reynolds number. They create these tiny pockets of turbulence right on the surface.
Wait, so adding turbulence actually helps? Isn't turbulence like a bad thing when it comes to airflow?
I know, right? It's counterintuitive. But in this case, that little bit of turbulence, it keeps the air flowing smoothly over the ball for longer, less drag. And the ball flies farther.
So golfers everywhere should be thanking Osborne Reynolds for those extra yards.
You could say that. It's a perfect example of how understanding and manipulating the Reynolds number can have real-world results.
This is incredible. It seems like the Reynolds number is like the key to understanding how everything moves through fluids, from jumbo jets to golf balls. But before we get too far ahead of ourselves, I'm curious, how did this all even come about? Who figured all of this out?
Well, it goes back to the man himself, Osborne Reynolds, back in 1883. He had this brilliant experiment, used a glass pipe, some water, and a tiny stream of dyed water.
Okay, I'm picturing this. What did he do with it?
So he injected that dyed water right into the center of the pipe where the clear water's flowing. At low flow rates, the dyed water, it stayed in a nice little stream, showed that laminar flow. But as he increased the flow, something amazing happened.
Look, don't leave me hanging.
The dye, it started to break up. Mixed with the clear water, it was visual proof of the transition to turbulent flow. And from those observations, he came up with the concept of the Reynolds number, a way to predict this transition in any fluid.
Wow, that's remarkable. This, simple experiment with dyed water, it led to this fundamental principle about how fluids behave.
Mhm.
That's quite a legacy.
Yeah, and his work has impacted all sorts of fields: engineering, meteorology, even understanding how blood flows in our veins.
Wow. The more we learn about this Reynolds number, the more I realize just how fundamental it really is. Okay, I'm ready to go even deeper with this. But before we move on, there's one thing I'm still wondering about. You mentioned that it can be used to understand how objects move through fluids. Can you give me an example?
Sure. Imagine a sphere falling through a fluid, like
Sure.
a tiny marble sinking in a jar of honey.
Okay, yeah, I can picture that.
Now, at low Reynolds numbers, the marble, it falls slowly and smoothly, at a constant speed. Viscosity is dominating here, and the drag force on that marble, it's directly proportional to its velocity. Pretty simple. But as we increase that Reynolds number, things get more interesting.
Okay, I'm intrigued. What happens next?
Well, as the sphere falls faster, or if we switch to a less viscous fluid like water instead of honey, the Reynolds number goes up. And what happens when the Reynolds number goes up? Inertia takes over.
So instead of a smooth, slow fall, it gets more chaotic.
Exactly. The flow around the sphere, it gets more turbulent. And that drag force, well, it becomes much more complex to calculate. It's no longer that simple relationship we saw before.
So the way an object falls through a fluid, it totally changes depending on the Reynolds number. That's wild. It's like there are two different sets of rules depending on the situation.
You got it. And that's why the Reynolds number is so important. It helps us figure out which set of rules to use.
All right, I'm definitely feeling a bit smarter about fluids now. We've covered pipes, airplanes, golf balls, felling marbles. It seems like this Reynolds number is everywhere. But I bet there's even more to learn, right?
Oh, absolutely. We've just scratched the surface. There are so many more fascinating examples of how the Reynolds number shows up in unexpected places.
Well, I'm ready to keep going. Let's take a quick break, and then we'll dive into even more real-world applications of this amazing concept in part 2 of our deep dive. Don't go anywhere. All right, we're back, ready to go even deeper into this Reynolds number thing. Before the break, we were talking about how this ratio can help us understand everything from airplane design to the flight of a golf ball. I have to admit, the more we talk about this, the more amazed I am by how, versatile this concept is.
Yeah, it really is remarkable how it pops up in so many different areas, and we've only just, scratched the surface of its applications.
Well, I'm ready for more. What other surprises does this Reynolds number have in store?
Okay, let's switch gears for a minute. Let's talk about packed beds.
Packed beds. Okay, now you've lost me.
So picture like a container filled with a bunch of particles. Could be sand or beads or whatever. That's a packed bed. And it turns out fluids often have to flow through these beds in industrial processes. Think filtering water or separating chemicals.
Oh, okay, so real-world stuff. So how does the Reynolds number fit into all of this? With these packed beds, I mean.
Well, just like with pipes or those airplane wings, it helps us understand how the fluid's going to behave, within that bed. It all comes down to the spaces between those particles and how the fluid moves through that, maze.
So at low Reynolds numbers, I'm guessing the fluid would flow smoothly through those gaps, kind of like a stream, meandering through a rocky riverbed.
Yeah, exactly. That's laminar flow. And it's often what you want in packed beds for processes that need really precise control, like filtration or chromatography.
Because with that nice smooth flow, everything gets processed evenly.
Right. But crank up that flow rate, and those inertial forces, they start to take over. You get turbulent flow. And now the fluid's swirling around, mixing more, vigorously within that bed.
I could see how that might be a good thing, though, in some cases. Like if you really need to mix things up.
Yeah, exactly. Like in chemical reactors, turbulent flow can be super useful to make sure all those reactants get in contact with the catalysts, speeds up the reactions.
So knowing the Reynolds number for a packed bed gives engineers a way to, fine-tune everything. They can basically choose if they want laminar or turbulent flow.
Yeah.
Depending on what they're trying to achieve.
Yeah, exactly. It's all about understanding how that flow is going to behave and tailoring it to get the results you want.
This is so cool. It's like the Reynolds number. It's like a secret code. It unlocks all these hidden complexities of fluid flow and in places you wouldn't even think of.
And speaking of unexpected places, let's talk about stirred vessels.
Stirred vessels. Is this like a giant pot of soup?
Not exactly. More like the large tank with a rotating agitator inside, like an industrial-sized blender.
Okay, I'm picturing like a scene from Willy Wonka.
Something like that. These stirred vessels, they're used for all sorts of things. Mixing chemicals, making food products, you name it. And of course, the Reynolds number is important here too.
I bet. So how does it work in this context? What's the, I don't know, what's the deal with the Reynolds number here?
Well, that rotating agitator, it creates these complex flow patterns inside the vessel. And the Reynolds number, it helps us understand how much mixing and turbulence is happening because of that agitator.
So low Reynolds number, gentle mixing. High Reynolds number, more vigorous churning.
Exactly. And just like with packed beds, the desired level of mixing, it depends on what you're trying to do.
Right, so for something like, I don't know, dissolving a solid into a liquid, you might want a high Reynolds number to speed things up. But for, like, delicate stuff, maybe growing cells in a bioreactor, you'd need a lower Reynolds number so you don't damage them.
You got it. It's all about finding that sweet spot for whatever process you're working with.
This is amazing. The Reynolds number really is like a universal control knob for fluid behavior in all these industrial settings. It's incredible to think that something so, I don't know, simple has such a huge impact.
It's true. And it's not just about industrial applications either. Remember that experiment Osborne Reynolds did? With the dyed water in the pipe?
Yeah, the one where he showed like visually how the flow changes from laminar to turbulent.
Right. Well, that experiment, it also laid the groundwork for understanding something super important in pipe design. Pipe friction.
Pipe friction.
Yeah.
Isn't that what causes like pressure drops in plumbing systems? Those annoying things?
Exactly. It's that resistance to flow. Causes energy losses. And guess what plays a key role in how much friction you're going to get?
The Reynolds number. I'm starting to see a pattern here. So higher Reynolds number means more friction.
Generally, yeah. As the flow gets more turbulent, there's more interaction between the fluid and the pipe walls, increases friction, leads to more energy losses.
Okay, that makes sense. So engineers have to factor in the Reynolds number when they design piping systems, right? So they can minimize those energy losses.
They do. In fact, there's this tool they use. It's called the Moody diagram. It helps engineers predict pipe friction based on, you guessed it, the Reynolds number and the roughness of the pipe.
So they can use this diagram to figure out like the best pipe diameter and flow rate and all that to make things as efficient as possible.
Exactly. Just another example of how understanding the Reynolds number helps us design and operate these systems better.
Man, this is all starting to click for me now. Pipes, packed beds, stirred vessels. It seems like this Reynolds number, it's like a universal principle behind all sorts of fluid dynamics.
Right? It is. It's this fundamental concept that helps us understand the world around us, from the tiniest, capillaries in our bodies to the vast currents in the ocean.
This has been an incredible journey so far. I'm ready to see what else we can uncover. But before we jump to part 3, one more question. You mentioned earlier that the Reynolds number isn't the only, like, dimensionless parameter out there. What are these other secret codes of fluid dynamics?
I'd be glad to talk about that. There are actually a whole bunch of these dimensionless parameters. Each one captures a different aspect of how fluids behave. For example, there's the Mach number, which, welcome back.
I'm ready to uncover more of these fluid dynamic secrets. Before the break, you mentioned that there are other dimensionless parameters besides the Reynolds number. What are they, and what kind of insights do they offer?
Well, we were just talking about the Mach number. It basically tells you how fast something's moving compared to the speed of sound.
Ah, the Mach number. That's the one we hear about when jets break the sound barrier, right?
It's super important for understanding what happens when things are moving really fast through the air. Like, at those speeds, the air can't get out of the way fast enough. That's how you get those shock waves and sonic booms.
So the Mach number helps us predict when things are going to get really loud.
You could say that. But it's more than that. It helps engineers design aircraft and other high-speed vehicles that can actually handle those, extreme conditions.
Okay, that makes sense.
Yeah.
So we've got the Reynolds number for that balance between inertia and viscosity.
Yeah.
And the Mach number for when things are moving super fast. Any other dimensionless numbers we should know about?
Oh, yeah, there are a bunch. And each one tells us something different about how fluids behave. For example, in open channel flows, like rivers and streams, there's the Froude number.
The Froude number? Okay, I'm all ears. What's that one all about?
The Froude number, it's all about the balance between inertia and gravity, how gravity affects the flow, and what happens at the surface.
So, like, it helps us understand things like how fast waves move on a river, or maybe how those whitewater rapids form.
Exactly. The Froude number is key for understanding stuff like that. It's super important for designing channels, dams, and other hydraulic structures.
It's amazing how these dimensionless numbers give us a way to, like, measure and predict all these complex fluid
It
behaviors.
really is. And the more we explore fluid dynamics, the more we find all these fascinating connections and relationships.
This deep dive has been an incredible journey. We've learned so much about the Reynolds number and its dimensionless cousins, and how they help us understand everything from pipes and airplanes to, rivers and even the air we breathe.
It's been great exploring all of this with you. It's amazing how something as seemingly simple as the Reynolds number can help us understand so much about the world around us.
I totally agree.
Mhm.
So to wrap things up, what's the one big takeaway you hope people get from this deep dive?
I think the biggest takeaway is that there's a hidden order, even in the most complex fluid behaviors. And if we understand these fundamental principles, like the Reynolds number and those other dimensionless numbers, we can not only predict how fluids will behave, but we can also design systems that actually use those behaviors to our advantage.
That's a great point. It's like we've been given this, like, secret decoder ring for the language of fluid dynamics,
Yeah.
and now we can use it to solve real-world problems and make some incredible things happen.
Exactly. So next time you see water flowing in a river, or watch a plane take off, or even just stir your coffee, take a minute to think about all those hidden forces at play. There's a whole world of fluid dynamics out there just waiting to be explored.
Well said. Thanks for joining us on this deep dive into the fascinating world of the Reynolds number. We hope you've enjoyed it as much as we have.